All right. Good morning again. I'm Peter Wieland. I'm the technical lead for the Window Driver Frameworks team. I have Abhishek Raman here, who's one of the developers on the team as well. He's going to answer the hard questions at the end. We want to talk to you today about why you should be using our driver frameworks to build your drivers. The first thing I want to say is maybe a little bit of I like to know the audience. So I'm assuming everybody here does hardware drivers. Raise your hands if you build hardware, write device drivers. How many of you have written Windows drivers before? How many of you have written WDF drivers before? Okay. For that last set, this is really intended for the people who have not used WDF to explain to them why it's going to be helpful. If you already know WDF, I won't be offended if you want to do something else with this hour. Feel free, because there's really not a lot of new, exciting WDF content here. It's really just the basics of how to use WDF to build a great driver. So to talk about this, we'll talk about a few of the types of drivers, how I break drivers down, talk about some of the challenges in building a high-quality driver, and how WDF is going to help with that. And my hope is, you're not going to come away from here and be ready to write a WDF driver. That's hard in an hour. My hope is that you'll come away from this, and when you have to do your next project, you'll remember, Peter said this is going to make it easier. I'll get it out the door faster. It'll be better. I should look at the technology he's talking about. I should see if we can adopt it. Start out, why do we want to focus on having great drivers? Because in reality, that's not what the customers notice, right? You want to put your time on mechanical engineering, industrial design, software to show off your device, packaging. There's a lot of stuff that goes into building a great device and a great device experience. And nobody really notices that driver. If you do a bad experience, they're not going to notice the great driver. They're going to notice the bad experience. If you do a great experience, who cares about the driver, right? Well, the problem is everybody notices if your driver isn't great. And as drivers, we're getting drivers to be better and better quality. We're building better tools to help end users and also to help OEMs track down problems. We're doing better telemetry so that you can see what your customer base is doing. And you can do the best experience in the world if it runs the user's battery out, if it crashes the system when they unplug the device, if it slows their machine down or they have to reboot it more often. They'll start to notice those things, and it's really, that takes away from that experience you tried to build. So you have to build a great one because you want to have that great experience, and this is an integral part. Types of driver models. So there's a lot of uses of the term driver model in the Windows documentation. We mean it to mean technology area. We mean it to mean sort of type of driver, as a print driver, display driver, these things. When I talk about it here, I'm really thinking about how do you go about building that driver? What's the pattern for building that? So if you think about our base driver model, we call it WDM, the Windows driver model. We're very imaginative. I think about it like a box. That box is the interface that WDM expects a driver to implement. WDM doesn't care what's inside that box at all. It just knows that there's this outside edge that it can talk to in various ways for plug and play, power management, manageability, I/O. And your job as a developer writing a full driver is to color in everything in that box. So you have to write that plug and play and power management code. You have to do the I/O handling. You have to talk to the hardware and set it all up. And then there's this little box over on the side, programming your device. That's the part that's sort of key for your business, right? You need to make your device work. That's where you want to be able to focus, but you have to do all this other stuff in the WDM model. We have alternatives. On the complete other end of the spectrum, we have the class driver. So the class driver is a driver we write for a known industry standard interface like USB controller, USB HID over I2C, these sorts of things. And we build a driver to do all of this. We build all those parts. It's sometimes a WDM driver, sometimes they use other technologies. The advantage here is clear. Like the lines of code you write to functionality ratio is amazing, right? You write nothing, your device works, it plugs into Windows. The downside is, you have to conform to an industry standard that we have a class driver for. So if you've done something completely novel, there's probably not a class driver for it. The other problem is that the class driver, while it's great, there's not as much room for differentiation as if you were to do a full driver. So there are ways to do it by writing other drivers and plugging them into the stack. Most of these class drivers have some extensibility points. Sorry. Most of them have some extensibility points, but you don't have that full flexibility you get by writing the full driver. And in between that, we have these sorts of, those are the endpoints, right? We have some gradient stops. So we have mini drivers and mini port drivers. These are areas where a particular technology team, say networking or input, has said, our drivers are too hard to write. We want to make it easier for our group of part of the ecosystem to do their drivers better. So we'll do some abstraction. In the mini driver case, they'll write a library that sits on top of your driver and handles the I/O, does some parsing of requests and things like that, but you still write a full driver. So you have good flexibility, but you have this thing that they wrote that you have to interoperate with. The other side is the mini port, which is a much more restricted model. So in the mini port, you will have this blue box, this blue library will take over more of the driver's functionality. The programming your device interface tends to be very specific to your type of hardware. The networking interface is send a packet, receive a packet. The storage interface is send a SCSI request, get a notification of completion. But those are technology specific, and they often have some assumptions. They often have assumptions about how the hardware works. So for example, the old storage model that I used to own, which was years ago and has been dramatically improved, let me say, but it really worked great as long as you had a PCI device with an interrupt that did SCSI. If you tried to do fiber channel, it didn't scale very well. If you did a virtual device or a USB connected device, something that didn't have an interrupt, it didn't work because we built the original model around hardware specific assumptions, and it just was hard to break out of that. So these are sort of the four models that I think about when I think about drivers. All of them are based on that full WDM driver model. So when we started the WDF team, we were looking at driver quality. How can we improve driver quality? And we said, we're going to focus on that full driver. Because if we can fix things for that full driver, we make it easier for everybody who doesn't fit into one of those other groups. We make it easier for us when we write class drivers. We make it easier to do some of the mini driver stuff. And we can start to improve more of the ecosystem over time. So we took that anatomy, the breakdown of the full driver, and we started looking at what are the parts that we really need to improve. So the first thing we said was that boilerplate code that you have to write to hook into all of those interfaces. Everybody writes the same code. Everybody copies it from a sample or another driver. There's bugs that just propagate like a virus. Okay, maybe I shouldn't use virus in this conference, but there's bugs that propagate through the code as it gets copied and changed. So let's get rid of the boilerplate code. It's just problematic. It's pretty much identical in every driver. We don't need to have it. Then we looked at the other areas. Now, like I said, programming your device, that's something that we can't control. That's what we need the driver to do. So we left that as is. But everything else, we've done abstractions around these things for the mini port models and the mini driver models. And we said, let's do the same thing here, but let's not make it technology specific. So we built a library that handles plug and play and power management and hooking up your hardware and doing I/O and a bunch of support objects. And you can use this to build your driver. And if you think of it as a scaffold that your programming device code can sit inside of. But we still have these lines from programming device to Windows driver model and hardware, because it used to be that your code, like, you really had to use WDM for everything. And we decided not to take over everything. We didn't want to be the mini port model, because what we found with the mini port model is somebody starts writing a driver, works great in the mini port model, and then they need to do something outside the box. And they have to go back to the beginning and start over because they can't get out of that box. So like I said, as long as you fit inside the box, it's terrific. If you don't fit inside the box, it can be a problem. So we didn't want that to happen. We have this notion that my complicated architecture term for it is conceptual scalability. But the idea is that you shouldn't have to go back to the beginning and start over in order to make a change, in order to make things more complicated. You should be able to just opt into the complexity as you need it. So we leave the ability to talk to WDM, we leave the ability to talk to the lower level hardware interfaces, but we tried to deprecate them where we can provide value, where we can provide better interfaces. And so that gives us WDF. We have two flavors of WDF. We have WDF for kernel mode drivers, KMDF. And this is our base model. This provides composable building blocks that you can put together to create that scaffolding. And when you build the scaffolding, we have default behavior built in for how your driver should work. So you build a scaffold and you get a fully functional driver. And then you can override that behavior. We have events that you can set callbacks for to change the behavior of your driver as you need to. And the other thing we wanted to do when we designed this was that we wanted to have very consistent programming patterns. So if you have written a WDM driver, you know that I/O manager programming patterns are different from the memory manager programming patterns, from the EX programming patterns. Like the names are different, the naming styles are different, the parameters are different, and it can be jarring to have to sort of remember all these subsystems that don't seem to mesh well together. So we wanted to have a very consistent pattern across all of WDF. We want to, like I was saying, we want to be able to start simple. You should be able to start with the simplest driver possible, and then you opt into the complexity as you need functionality. I hate complexity in code. Every time I see complicated code, I get the willies, because I know there are bugs hiding in there that I'm not going to find. I can test it as much as I want. I can have my whole team review it. There's a bug in there somewhere. And if I can't keep the whole thing in my head at once, something's not good. And so I really like anywhere where you can get complexity out of code, I think we have a big win. This may say something about my programming skills more than my philosophy on code, but there it is. And then, like I said, we didn't try to wrap everything. We didn't want to become the NDIS model, which is a great model, but every time new system APIs get added, every time new kernel APIs get added that might be relevant to NDIS, the NDIS guys have to add those into the NDIS API. So you just see duplication of APIs where they're not really doing anything unique with it, they're just passing it through to the kernel. But because they have that restricted box, they have to plumb those APIs through themselves. So we focused on the common scenarios and where our abstractions could be useful. And for everything else, you can escape out to WDM. We will give you the native WDM objects off of any of our objects. You can go to WDM and make the calls you need. Now, that's an advanced thing to do, so you have to do that in the right ways or you can cause problems. But the ability is there. We also have a version of WDF that runs in user mode. I should say the kernel mode version we've had since XPSP2. This is not new technology. We've been building this up release over release and adding to the capabilities. The user mode framework we've had since Vista. This is like the 4th release, I think, of user mode drivers. And it's a subset of the kernel mode framework. Not all of the kernel mode framework lifts up to user mode, and then there were some engineering challenges in the way we built it, and we haven't quite smoothed some of that out. But it is a pretty full subset of what you can do in KMDF running inside of a user mode host process. Now, when we designed this, the place where we were focusing was new developers. What we had seen when we talked to people were a lot of application developers were getting drafted to write the driver for their group, right? So they didn't, or a lot of new developers out of college, they'd come in and that was their project, was to write the driver. So they went from learning application technologies, C++, COM, these sorts of things, into this kernel area, which is daunting. It's a different environment. There's a lot more to learn. In the end, it's not that scary, but it can seem very frightening when you first drop into it and you really don't know, like none of the patterns you're used to apply. So we wanted to have a familiar development environment, something where the COM patterns would apply, something where you knew how to debug because you could use the regulars debugger. And we also wanted to do this because we get isolation. So by moving your driver into user mode, we can isolate the user from issues in your driver. Ideally, none of our drivers ever crash or corrupt data. In reality, our drivers crash and corrupt data. They're software. They tend to be pretty large, complicated projects, and I've explained my thoughts on that already. So there are bugs in there, and they're going to hit users. And by running these things in a host process, we change the experience. It's still not a good experience, right? If they unplug your device, or you plug your device in, and it's working for a little while, and then something crashes, they lose access to the device for the little while. They'll have to restart the app that was using it, probably. So it's not a good experience in and of itself, but compare that to a blue screen or leaking credit card numbers or getting the machine rootkitted because of a security bug, it's a lot better than it could be. So the way I think about it is your customers will not know that they could have been more unhappy about this. But you'll know. So you're saving yourself some support costs by moving to user mode. The other thing that's really great about this, and I love this, is this isolates me from the crashes. So when we finally got UMDF up and running and I was writing my first sample, I first did what I would normally do with the driver, which is like I went to my development machine and I wrote my code and then I moved it over to my test machine and I plugged my device in and I debugged it there for a little while. And I did that for like a day and then I had to go home. And I thought, I'll just bring the card home. And I sat at home with my laptop on my couch and I watched some TV and I plugged the card in and I wrote a driver for a USB device on my production work laptop, and I never had to worry about the system blue screening. Didn't have to worry about rendering it unbootable because I had this driver with a bug during the initialization code. So I really love being isolated from that. I really love being able to just do single machine development. Now, UMDF is not supported for all hardware classes. We have driver-to-driver interfaces in Windows that are not real amenable to going to user mode. And so the UMDF team has been going sort of block by block. We go to teams and try to figure out how we can get their technology up into user mode. Can we write a shim? Can we change some of the I/O controls? Can we add some functionality to UMDF to fix some problem with their particular technology? But we have a white paper, it's at the end of the deck, that talks about what technology areas work for UMDF and which don't. And we actually have driver technologies now which have to be in user mode. Portable devices, sensors, those have to be in user mode. There is no kernel mode equivalent. So Peter, you've been telling me how easy the drivers are going to be to write, but maybe you don't believe me. So let's take a sample project. And my requirements are, it has to be a fully functional driver. So it should do plug and play and power management. It should be something I could install on any USB device. It doesn't have to do anything, but I should be able to install it and like unplug the device and plug the device in, plug multiple of the device in, all the things you would do with sort of your first driver, and it should work. And it should be written using KMDF because KMDF fits on the slides better. For better or worse, UMDF is a little more verbose, and I couldn't quite compress it and make it readable. So we stuck with KMDF for this. So here is our functional driver. I hope you can read this. We have this function called driver entry. This is the entry point for drivers. And its job is to create a driver object. The driver object has one important callback, which is what to call when attaching the driver to a particular device. That's called the EVT device, driver device add call event. So we register an on-device add function to call when that happens. And then we call WDF driver create. Now there's a pattern that you'll see throughout all of this, which is WDF noun verb. So WDF driver create creates a driver object. Any other object you want to do, WDF name create. This one takes a config structure which has additional optional parameters in it. That's it. That's driver entry. So the on-device add function, how does that work? Well, that gets called to attach the driver to a device stack, and all you do is create a device object. That's it. This is the entire driver. This is 25 lines of code. This is the amount of boilerplate you need to write a driver. And the other thing that I like about this, you may notice there's no cleanup code at all. In a WDM driver, I mean, this equivalent WDM driver is at least 300 lines of code. And a lot of it is just you copy it from somewhere because you have to write it every single driver. Right? And in the WDM driver, you have to handle a bunch of error conditions in this path. You don't have to handle them here. If you return an error from on-device add, WDF will clean up the objects for you. And that's, if for those of you who have written drivers, you probably know that that's one of the big problem areas with writing drivers, that you have a lot of state you have to keep track of. Thank you. Since drivers are very dynamic things, we have requests coming in, we have P&P operations happening, you have devices arriving and devices leaving. In the worst case, this is all happening at the same time. So there tends to be a lot of state that you're keeping track of, state with requests, state with the device, state with handles. And it gets to be a lot to keep up with. And it gets worse when you have to add in proper error handling for out-of-memory conditions and other sorts of transient errors. And it's really important that you manage that state correctly because you're running in a shared address space. For a kernel mode driver, you're running in the kernel. For a user mode driver, you're running in a host process with other devices. And if you run that out of memory or if you crash it, it takes everything down with it. So this was one of the key areas. There's 3 key areas I'm going to talk about where WDF, we looked at how could we really change how this worked for drivers. So this was one of the key areas, and we automated this through our base object model. So WDF objects make up our API. We have sort of opaque handles to them. It's all a C API, but we use opaque handles, and then objects have methods, properties, and events that you can register callbacks for. WDF knows the lifetime of most of these objects and will delete them automatically when they're no longer relevant. So in the case of the WDF device, when your device is unplugged, plug and play tracks WDF tracks all the plug and play operations. It knows when the system is done with your device object, and it will trigger deletion automatically. So that's great for the WDF objects and tracking them, but for your own data, you can add a context to any WDF object. In fact, in KMDF, you can add multiple contexts. UMDF, you can only do one context. So the context is space you can use to store whatever context you need about that object. Pointers to other data, state variables, names, anything you need to track. The context is freed when the object is freed. And I talked about default behavior and customization. Our default behavior is to just free the context. There are 2 events with every object that you can register callbacks for to customize the deletion. They're sort of the same thing. They happen at different points during the deletion path. They're called cleanup and destroy. So if you have a pointer to something that you need to deregister with a kernel service or some other driver service, if you have memory you need to free that you've allocated on your own, you can add these cleanup callbacks and then go delete it. And I said WDF knows the lifetime of many of the objects itself. For objects, there are some objects that you create that you can delete manually. WDF object delete, WDF noun verb. And when you delete an object, or when WDF deletes an object, that takes care of that one object. But objects can have children. So we have an object hierarchy that goes from driver down through devices and then other objects underneath those. And with that, when you delete an object, all of its children get deleted automatically. We actually run through the tree. We call the deletion callbacks. We look for objects that say their callbacks have to be run at passive level. And if we're at dispatch level, we'll move that entire deletion operation to a thread and run it at passive level for you. Which, if you know WDM, will hopefully sound like a really great thing. And if you don't, I may have just confused you. But apologize for that. So we clean things up automatically. So you delete the object, everything gets cleaned up. I wanted to show 2 examples of this. Can people read this? I didn't actually go to the back of the room to make sure. I hope this is legible. And this is deleted. I couldn't fit it all in one slide anymore. So you define a context structure. This structure is whatever you need to keep track of for that object. We have a macro that will then declare that structure as a context type. And if you had multiple contexts that you'd wanted to do on a particular object, you would just declare another structure with a different name and use this macro again to make it another context type. And as part of this macro, you can define a function that you use to get the context off of an object. I said objects are opaque handles, so this is how you would get your context out of that object. I call it get device context. I'm imaginative. So when you want to go create your context, you have to set up object attributes. Object attributes are common to every object. These are the parameters for sort of the base object. And one of the things that's in there is the context. So we have this WDF object attribute structure. You'll see this a lot as you write WDF drivers. And like every structure we have an init macro. So this initializes the object, sets all the default values, and it sets a version so that if your framework driver written against framework 1.11 in the future runs against framework 1.13, 1.13 knows you're a 1.11 driver and knows not to expect any new parameters we added. We are very big on forward and backwards compatibility in that way. So in this case, we call the init macro, and this init macro also specifies the context type. So we provide that as a parameter. And then for no particular reason, but just to demonstrate, we'll set a destroy callback. So this is an event function pointer inside of the attributes. And then when we create the device, we just provide the attributes in the parameter instead of WDF no object attributes. And then once we've got the device, we can use get device context, get the context off the object, and do our initialization. And if that initialization fails, you can just return an error from on-device add. WDF will clean the device object up for you because it knows that when on-device add fails, the device object's no longer needed. Its lifetime is over. So the other thing I wanted to show was how to create a child object. I'm going to make 2 child objects here. First, I'm going to make something called a USB target. These are how you would talk to a USB device. If you're in a USB stack, this is how you would talk to the device below you. It helps with request formatting and processing requests through. So we're going to make the USB I/O target. Now, here I'm not specifying object attributes, so this gets the default parent, which in the case of an I/O target is the device. Then we're going to make, because to work with the I/O target, we also need requests, which represent that work we want the lower driver to do. So we're going to allocate a request. We're going to make this a child of the I/O target. So we initialize some attributes, and then we set the parent object and the attributes to USB I/O target. And then we create the request. Provide the attributes. WDF will now make this request a child of the I/O target. And now, just to sort of walk through this again, right? If your device is removed, WDF will delete the device. When it deletes the device, it will delete that context that goes with the device that we set up earlier, and it will call that destroy callback. It will also delete the USB I/O target because that's a child of the device. It will also delete the request because that's a child of the I/O target. In deleting the request, it will free the context that goes with the request. If we had a cleanup callback on the request, it would call that cleanup callback before getting rid of the context. So you can use this to build trees of objects, support objects, and then free them when operations are done. It makes things a lot simpler in drivers compared to how you would do this in WDM, where like for every ERP, you would have a pointer in there somewhere to some structure that you would allocate it, or maybe it was in a table, and then you would have to remember like what you've initialized in that, and did you free it, and where were you in the execution chain. You have to null initialize all your pointers so you know to check and not free them. I found it to be incredibly liberating. And in addition to all of our other objects, we have a WDF object, just sort of a base one. So if you have anything that you want to just track as a child of another object, you can just make a WDF object, add a context to it, and track all your data on that context. So simple little drivers, nice, fully functional driver, except it doesn't do any I/O. So the client could open it and try to send it a request, and that request will fail. It doesn't do anything. And once you enable I/O, for those of you who have written drivers, know this. Sorry. Once you enable I/O, I sort of liken it to those cartoons where somebody opens up the fire hose and goes and like throws them all around the room, right? You have to deal with, in the worst cases, you have to deal with lots of requests, potentially invalid or even malicious requests coming from multiple clients at the same time, along with plug-and-play operations, along with P&P operations. You have to validate all of those requests, and you have to handle potential cancellation of those requests and rundown of those requests when handles get closed. There's all sorts of stuff, right? As soon as you turn on I/O, tons and tons of complexity that you have to deal with in WDM. And the other challenge is that you're supposed to do all of this in an asynchronous model. The Windows driver model pushes asynchronous I/O. It's asynchronous by default. So you get a request, you're supposed to do the minimal processing before you can either queue that request or push it to your hardware, and then you give that thread back to the client so it can do work with it. And that way we don't have clients who have to create tons of thread to do concurrent I/O or concurrent processing. We can use thread pools that have very few threads. And if you're blocking a thread, you're not really tying up CPU, but you're still tying up memory resources and a lot of other things. So it's nice to give the threads back. So you have to do all this stuff, and you have to do it asynchronously. And this was something we took the experience we had doing other drivers and other abstractions we've done, and we turned this into two core objects. We have I/O queues and we have requests. So I/O queues coordinate flow of I/O through the driver. The idea is that you can use these, you can create one queue or multiple queues, so you can use them to collect work or distribute work through your driver, or distribute and then recollect. You can set different execution modes on these, so you can say this queue should dispatch requests one at a time to me, or this queue should just let requests through in parallel. You can actually say this queue should let like 6 requests through at a time, but no more than 6. You can adjust that limit as you run. The only thing you have to do, you can create multiple queues. The only thing you have to do is create some top-level queue, one or more, so that WDF can hand you I/O. That's WDF, when ERPs come in from the I/O manager, WDF looks for a queue to dump them into. If that queue is idle, it will run the I/O automatically. If that queue is busy and it's a sequential queue, or if it's stopped, then WDF will just push the work into the queue and leave it there. So we use these as gates to control flow through the driver. You can use them as gates too. You can stop them and start them in order to control the flow. So if you need to shut down all I/O through your driver while you do some background operation and then start it back up, or a recovery operation, you can stop the queue, go do your work, and then restart the queue, and I/O will start up again. I said the other object we had were request objects. So queues manage the flow of work. Request objects represent that work. These are packetized I/O. WDM has packet-based I/O, which really helps because if you don't have to sort of squirrel all the parameters away in your own structure and then hold on to it. We sort of provide it for you in a packet automatically. And we looked at these. These are called ERPs, or IO request packets in WDM. And we made them into objects because every time we've ever worked with an ERP, we have to track context. We have to track helper objects that go with that request. We need something we can push into a queue. We need something that we can synchronize around. So we made it into an object. You can add context in children, just like any other object. There are some strange rules about how requests get deleted. So there are rules about what you can parent under a request or put underneath a request. We have methods on these that help with the validation of the payload. Now, this goes into that your code sort of thing, right? You know what your interface is. You know how to validate those parameters. We can't do that for you. We don't know what a particular request is. But we have some methods that help doing some basic validation on the packets. And the other thing that requests do is we have one place now where we can manage some of the race conditions that occur, particularly around cancellation and completion. So instead of when you need to do cancellation, you tell WDF, this request is now in a cancelable state. And here's the callback for the cancellation event. When you need to, you could do that like while your request is sitting on the hardware. When the request completes, you go back to WDF and say, this request is no longer cancelable. And WDF will do a lot to manage the race conditions that can occur if, while you're doing that, the cancellation comes in. So I want to look at how we set up I/O in a driver. It's, I think, pretty easy. So we have to make a queue. We'll make a top-level queue. So we're going to start with a queue config, because we need parameters. There are parameters that go with the queue. We're going to call the init macro, and this version of the init macro makes this the default queue. And this queue we're going to make sequential. So this will dispatch requests one at a time. We're going to register one handler for device control. So reads and writes that come to the driver will get bounced with an error because we don't have a handler for those, but device control requests will come through. And then we create the queue. This will be a child of the device. That's the default parent. Now, let's look at that device control handler. Right? This is the function that gets called for each of those requests that comes in. This one's really simple. It only supports one ioctl. That's pretty nondescript. A real one would have a switch statement or a lookup table of control code types. And the first thing we're going to do, since it's telling us to do something, we're going to get the input buffer and find out what we're supposed to do. So the assumption is there are some parameters that come with this. And one of the things that we do when you retrieve the input buffer for a request, you can tell WDF how big it needs to be. So this is one of those small things that simplifies the validation. Is you get the input buffer for the request, and if it's not big, if the buffer wasn't big enough, if the client didn't send you enough data, you'll get back an error, and you can just put a failure point right in here in your code. And then the rest of this is just sort of what a driver would do. You validate all the parameters in there to make sure that it's not something malicious. And then you start the request running. So you either queue it to a queue for some deferred processing, or you send a request to the USB device, or you poke a register on your hardware and set up some operation. And then you return the thread back to the client so it can do its own work on it, do processing, send more I/O, put it back in a thread pool. Later on, there's going to be an asynchronous callback, an interrupt, or an I/O completion. And there your driver will get control again. You'll finish up whatever processing you have to do, and you'll complete the request. If you get an error in this code path, I have some if failures. Like I said, this doesn't compile, but we have some failures, and those all go down to the bottom, and we just complete the request. When we complete the request is deleted. When it's deleted, any context or child objects get deleted as well. And when you delete this, when this request gets completed, that frees the queue. So now the queue can dispatch another request to you. Now, if we wanted to be more complicated about this, we'll go into some concurrency. Queues really changed the way I thought about concurrency in drivers. And when I talk to new developers about drivers, particularly people who are sort of new to system development in general, their first thought usually when you talk about concurrency is, oh, we'll add a lock. We'll have that thread block until the lock is free, and then it can go do its work. Right? This is sort of the simple traditional view of concurrency. The problem with that is you're tying up those threads, and you want to give those threads back to the apps so they can do work without spinning up more threads. More threads means more memory pressure. More memory pressure means slower machines, bad customer experience. And we have tools that are getting much better at figuring out where that pressure is coming from. So you want to give that work back. So the way I look at all of these problems now, and particularly in terms of I/O, is I look at it first as a serialization problem, not a synchronization problem. Can I define a domain in my driver and protect it with a queue, a sequential queue, and just have that queue deliver work to my driver one at a time? As long as I use that as a gate, I can safely access the hardware without needing a lock, because I won't have any other path where I could be accessing it again. So in our example, you can use queues then. You can use parallel queues and distribute work. You can collect work with sequential queues. In the example we just saw, if you wanted to have read and write operations that were serialized with device control operations, you'd add read and write handlers to that default queue. If you wanted to have read and write operations that are serialized with respect to each other, but then have device controls be serialized on their own, you could make a second top-level queue, make it a sequential queue. You call WDF and configure request dispatching and say, put read requests in this queue and put write requests in this queue. And then when a read or write come in, they go to that queue and they're serialized together. When device controls come in, they go to this queue and they're serialized together. And now that you have a gate and you have like two things that could be trying to access the hardware, now's a much better position to put a lock in, because you don't have some unbounded number of things that are contending for that lock. You have like two operations, and you could put that lock in, or you could have that work then funnel through another queue to protect the hardware. So once you reach the limit of what queues can do, and queues are really about serializing everything with respect to I/O. If you have to serialize for asynchronous operations, you can still use the queues as a gate. You could stop them, wait for all the I/O that's outstanding to finish, and then go do your work, knowing that the queue won't let anything through. But we do have some locks. We have a wait lock and a spin lock, which are two of our sort of lock primitive objects. But you can also just lock a WDF object. And when you lock a WDF object, it grabs what we call the presentation lock, which stops. There are some exceptions to this, but in general, it stops the callbacks on that object until you drop the lock. So if you need to synchronize with respect to another one of your object callbacks, you can grab the object lock, do your work, drop the object lock, and you know in that period no other object callbacks are going to come in. And the goal here really is to limit the amount of blocking you do. We want to do proper synchronization and make sure you handle all of that concurrency, but you don't want to do it by tying up the client's threads. And worse, you don't want to do it by tying up some arbitrary thread you happen to get called in. Like stealing one of your client's threads is it's not good. Stealing some thread that you just happen to get called in can be really painful. It causes like weird glitches in the system if you hold the threads up for long periods of time. So the last area I wanted to talk about in terms of improvement is power management. I think the politest way to describe our power management system in Windows is that it's very rich and nuanced. And power management is absolutely critical for great experience these days. If you remember the machine Mike Angiulio opened up, the tablet that he opened up, it's like 2 to 3/4 battery, right? That's the last frontier for us, is how much power can we get out of these things. So when drivers run batteries down, that results in a bad user experience. But Windows rules for power are so complicated that there aren't a lot of drivers that really get every part of it right. We have best practices, but they're hard to implement. And what we see is either drivers that don't power off when they're not in use, which means they run the battery down, or they don't handle the edge cases. So they can stall the power system and cause a 9F bug check, where we just can't make progress on power because we rely on the drivers to all be good citizens. Drivers are part of the trusted computing base. They're part of the kernel. They really have to behave as good citizens inside of the kernel. So if a driver doesn't handle all those edge cases, it can result in all sorts of weird behavior. And the worst version we see of this, we see this during development while we're building new drivers, is you like close your laptop and you throw it in your bag and you think you're fine because your laptop's going to go to sleep. But actually one of the drivers crashed and the system rebooted and woke up and came up to full power, not asleep, and is running in your bag, and you find this out like 3 hours later. And if you're lucky, your battery's dead. If you're not lucky, you have to call support and get a new system board because you fried something on it, right? So I can't stress this enough. It's very important that drivers follow the power rules, and it's very unfortunate that WDM has made that so hard. I got some telemetry data. From the telemetry we see, 10% of all of our driver crashes are related to power management. And these are just the crashes where we can deterministically say something blocked the power engine and couldn't make progress. This doesn't cover just like referencing an invalid pointer during a power operation. This is specifically like we blocked the power sequence. So clearly this was something we would want to focus on in WDF because we'd all written this power code and we all hated it. It was painful. So when we looked at it in WDF, we looked at how could we make this a more declarative model. What we'd like to do is have the driver just tell us what its power capabilities are. We'll define some events around those power operations. The driver can register callbacks for it if it needs to customize the behavior. Otherwise, we should just have a default driver that can power on and off according to the system state and the S and D state transition rules. So you declare this, and then we have a state machine that handles this all automatically. To be clear, we have 4 power state machines internally, 2 plug-and-play state machines. I think there's an IOQ state machine that gets involved in this, and then there's something else for idle detection. So there's a lot to track here. We used to put it up on the slides, and on this screen, the state machine diagram is illegible from the front row. We stopped showing it because I think it was just too scary. So we handle all the OS power change operations for you. The system calls WDF and says, we're putting the system into a sleep state or we're coming out of a sleep state. And WDF manages those parts of it for you. It translates all of that into this set of simple power management events. And then you can override the behavior on those events to do power on, to do power off, to arm for wake, to disarm wake, or to say, tell the system, I'm the driver that woke you up. I need to be serviced. Now, like I said, we can handle all of the system level requests as to the system is going to sleep, so these devices have to go into a low power state. System is woken up, so these devices could power on. But the thing we can't do in WDF is know when the driver actually needs power. That goes into that programming the device. We really don't know if on any particular I/O operation you need the device to be powered on or not. So we define an attribute on queue called power managed. We're already using queues as gates. We can shut them down for power operations to stop I/O flow. So we said we'll make an attribute on a queue. You can make a queue power managed. When there's work in that queue, we know the device has to be powered on. When there's no work in that queue, we know it's safe to power the device off. You can set this attribute on multiple queues. So it's not just one. And I believe the default for a driver will be that your queues are power managed. So for most of the drivers you're writing, unless you're doing filters, you'll have to opt out of it if in particular cases where you don't need that. And the queue is a gate, so when I/O comes into a queue and the device is powered off, we will stop the I/O flow, power the device back on if the system's in a state where it can be powered on, and then we'll let the I/O go through. If there's I/O outstanding when a system transition comes in, say the user closes the lid, we will hold off that system transition for hopefully a very brief period of time while your driver finishes up that outstanding operation. Unless you register the special callback for the event that lets you say, hey, these requests, I can handle them in a low power state, so go ahead and power me down anyway. So you can customize the behavior as you need more complicated capabilities. So WDF manages a lot of this for you. The best case is the default behavior for a driver is you are not supposed to power back on after a wake until you have work to do. We don't want to power everything on in the system just to wake up and then try to power it back off. So WDF will handle if an I/O comes in while you're sleeping the machine, if it's running, we'll let that request go and then we'll put you in a low power state. If the system state transition comes in first, we'll hold that request off until the system is asleep and has woken back up and the WDM tells us we can power the device back on. Then we'll notice there's work in the queue, we'll power that queue back, power your device back on and issue the I/O. If there wasn't any work pending, we'll leave your device off until you have work to do. The idea would be that you would use power managed queues close to the hardware, so where you really need to touch hardware or where you need to synchronize somehow with the state of the hardware. And when we know whether or not your device needs power, then the next logical step was, well, why don't we just power the device off when it's idle? So WDF can turn devices off automatically. You have to opt into this by setting what we call S0 idle settings. If we were designing WDF today, we probably would have made this opt-out, not opt-in. But at the time we made it opt-in, and like I said, we're big on compatibility, so we're probably not going to change that default in the near future. So you need to opt into this idle detection. And what you do is you tell us what power state you want to go into after how long, and whether or not you can wake up the system. And in terms of how you wake it up. WDF knows your device is idle because all your power managed queues are idle. When that happens, we start a timer. When the timer expires, we'll tell the system we want to go into a low power state. If I/O comes in while that timer is running, we'll cancel the timer and just leave your device powered on. If I/O comes in while we're in the power state transition, we'll power your device off, then notice that there's work to do and power the device back on. right? These are the race conditions that WDM drivers have to deal with in power. And WDF handles these for you entirely automatically. And you, driver, can stop and start this. So if you have background work that you need to do, please don't have timers. Timers are evil. But if you have background work that you need to do, you can stop the idle detection, which will power your device back on if it was off, do your work, and then restart the idle detection, which will let you go back down into that low power state. So this is one where I really did want to show how easy it is to do. We're going to initialize plug and play and power management event callbacks are all together in one structure because typically a driver sets them together. They have some relationship. So we initialize the callback structure. We have that standard init macro. We set on D0 entry, which is what gets called to power your device on. You would restore any volatile settings that might have been lost while you were off. Set a callback for D0 exit, which is what gets called when you leave that working power state. You would save any volatile settings that are going to be lost, and then depending on your device, you might have to do a device-specific operation to turn it off. And then we set the power event callbacks. Now, there's one thing I wanted to call out here, which is normally for an object, we would have a config structure, right? I said that's where the optional settings go. There are a number of settings on devices where we wanted to move the errors in setting those properties up closer to the point of failure. So if you set the name on the object, or if you were to misset some set of properties, what we didn't want was a failure that occurs all the way at the end of the function when you create the device that you can't track back to a particular bad function call. So for device objects, we have this device init object. You set a bunch of settings on the device init object, and then you use that to create the device. So we do this before we create the device. Then we create the device. Now we have a fully power manageable device object. And then we want to opt into idle detection. So we'll initialize the idle settings with our nice little init macro. In this case, I said it's a pretend USB device. So we'll say we want to do USB selective suspend, which is this kind of strange USB thing that says, I can wake the system, but only if every other function on my device is powered off, because I have to be in my whole device has to be in a low USB power state for my wake signaling to work. Otherwise, you have to leave me on, because I won't be able to get that wake interrupt. There's also I can't wake and I can't for non-USB devices. We'll set a timeout of half a second. The default is like 5 seconds, so you probably want to pick a timeout that you know you can save power on. So you want to know roughly how much power it takes to power your device off and how much it takes to power it back on, and kind of figure out how long you would have to be idle for that to be worthwhile, and that's your idle timeout. And then we assign the S0 idle settings to the device. Now, just another pattern I want to point out. I said objects have properties. We have get and set methods like we have on the device init structure. Those set and retrieve properties, and they can't fail. They'll return the value or they'll set the value. You can just call them and keep going. Assign and retrieve are used when you need to do operations on an object that can fail to set something. So anytime you see a function where the verb is assign or retrieve, there's an error code that you may need to check. So in this case, if there were an error, we just return status from on-device add. WDF cleans up everything for us automatically. But at this point, we have a device that will shut down after half a second of idle time. So in the end, what do we have with the driver frameworks? Well, our goal was, I talked about conceptual scalability. I talked about making this easy to use. In the end, what we really want is that you can focus on controlling your device. The WDM driver, you spend a lot of time focusing on how to manage the OS. We really just want you to focus on how you control your device and try to leave everything else up to WDF. If you're using KMDF for your driver, over WDM, it's going to significantly reduce the size and the complexity of your driver, which means faster time to market, easier to support, easier to maintain. Better customer experience because there will be less of those hidden bugs. If you can use UMDF for your drivers, you're going to get that more familiar development environment, which may be very useful if you're new to driver development or the person you have working on this driver is new to driver development. You can do it on a single machine. It's not applicable to all driver classes, like I said, but where it's applicable, it's significantly of significant value. And both of these, whichever one you pick, they're going to let you get that high-quality driver. They're going to let you get it out to market quickly, and it's going to be more reliable than it would otherwise. So for those of you who haven't written drivers before or have just done WDM drivers, what kind of driver do you need to write? I showed you 5 models now, and which of them really works? And they kind of all apply. This is the decision tree I think one would use. If there's a class driver for your device, type of device, use it. If If you need to change your firmware a little bit to conform to that interface, do it. You'll save yourself so much time and money by just using the in-box drivers. And you can still customize by writing your own drivers, plugins, things like that. So if you have the choice between writing a monolithic driver or a driver that uses our class solution that uses our class driver, and then another driver to just expose the unique functionality of your device, do that. That hybrid solution will be better than writing your own monolithic driver, even if you're using WDF. Likewise, if you have a driver already that's WDM and it's working and it's not a support nightmare for you, it's not a customer experience nightmare for you, I wouldn't honestly rewrite it using KMDF just for the heck of it. If you have code that's working and tested, churning it for no other reason than to switch to KMDF is probably not going to help you. You should have a reason to make that investment. Now, you could look at your driver telemetry. There may be that reason in the telemetry. If you have to do this, what I called a full driver, I missed one. If you can't use a class driver for whatever reason, like there isn't one for your technology, look at the documentation for your technology area. See if it has a mini driver model or a mini port model. If it does, you should use that if it fits your type of device. Again, you're going to be able to leverage a lot of domain-specific code that's going to help you get that driver to market. And WDF support objects, we have a mini port mode. You can use, for mini ports, you can use some of the object hierarchy and things like that to simplify your work. For mini drivers, you can use the mini port mode. We also have written shims for things like HID and some networking so that you can write a full KMDF driver and then we'll fit it into the input stack for you. If you have to do a full driver, try using UMDF where you can. When you find you can't do it, send us mail. We like to know where people are trying to use it and where it's not applicable because, like I said, we have to go sort of point by point to figure out where to drive this. So when we get the feedback that says, I want to use UMDF for this type of driver and I can't, that gives us some idea of what direction we need to head next. If you can't use UMDF, use KMDF. You should never, ever have to write a WDM driver. I will be very upset with you if you write a WDM driver. Now, this is a talk statement, right? So, yes, there are still probably some spots where you might have to write a WDM driver. If you find yourself in one of those spots, send us mail and tell us, and we can have a nice discussion about whether that's really a WDM driver or one of like 10 other types of drivers in the system that aren't really device drivers. But we may also be able to help you figure out how to do it. We're very invested in getting you to use these tools. We want to have good driver quality. We want to have good user experience. So if we can figure out a way to make your driver work, we have a development team that can help out with that. Just don't send us code. We can't look at code. I want to go back to this point. I kind of like this point. It is a big investment to write a driver. It's a big investment for us for the drivers we write. We know how hard it is. And we have people who just do that. We know how hard it can be for a hardware company to write a really high-quality driver, along with all of the other things that go into building a good device. But it's important to understand that this is really part of making that good device experience. This is not something that you just have to do in order to get your software out. This is really a key part of the experience. And it needs love, it needs care, it needs some investment to make sure that it's good. There are some related sessions. I'm not entirely sure who added the USB devices into that, but if you want to build USB 3.0 devices, there's a good session on that. We have a talk right after this in the room from the WDK team about how to use Visual Studio to write drivers. If you're new to this, even if you're not new to this, you should stay for that talk. What the WDK team has done is amazing in terms of changing our tools and our tools story, and you should come and listen to that. There's a Chalk Talk tomorrow, I believe, about the developer workflow. So if you want to get into sort of a more discussion about how to use drivers and driver tools, there's that Chalk Talk. And there's a hands-on lab. It's all the way at the end of the expo hall, like past the big server, maybe past the curtains and the steam tables, I'm not sure. But I talked to the lab guys there, and they sound kind of lonely. And if you want to get started with these tools, if you want to try seeing how easy it is to write a WDF driver using Visual Studio and the templates that they have, go to the hands-on lab. I hear it's about an hour and a half, and you come out of it with a functional KMDF driver that you can play with. And there are people there who can help you understand how to use the tools and get things working. We also have some additional documentation. The one I wanted to make sure to mention was the WDF book. Now, this is a little bit dated. If you click on this link, it'll take you to O'Reilly to order the book. It's available only in electronic form now. We wrote this in the Vista timeframe, but it's a little dated, but it's still incredibly relevant for WDF. And for anybody starting with WDF, you should buy this book and read it. And to support that, we have a 50% off coupon code. So if you put in DDWDF, I haven't tested this myself, but I'm assured that when you do this, you'll get half off. So the book comes out to about $25 or $27, which, considering that it's like this thick, it was the biggest book we could get it was the biggest book MS Press could print in a single volume when we did it. So there's a lot of pages there for your money, and they're all good. We have design guides in the WDK for both doing kernel mode and user mode drivers. So these are another good sort of getting started point. These are a little, they are the getting started point, and there are reference guides to go along with those that document every API and how it behaves. And then we have this documentation point I talked about how you would pick a driver model, what kind of driver to use. If you sat through all of this for new to Windows 8 WDF content, thank you. We have a white paper for you. It will talk about some of that. I encourage you to read it, and then you can send us mail at wdfinfo.microsoft.com. This goes to me and the development team and the test team in WDF, and like I said, we are vested in getting you guys up and running with your drivers. So if you have questions about how to use WDF, if you're seeing a problem or something to bug, there are forums, there's online forums, there's if you look under the forums link on I'm getting ahead of myself. There are forums for this too, but you can just send us mail, and we'll try to help you out. Like I said, don't just send us your code and say it doesn't work. We'd like to talk about what you're doing and understand why and what the problems you're having are. We also have some blogs. I started a blog several years ago. One of my coworkers did as well, and then we had kids and found out it doesn't leave a lot of time for blogs. So they're a little stale. We want to start refreshing them. There are a couple others in the development team who have done blogs as well, and I couldn't fit them on the slide. So if you click on WDF, that's a link on MSDN for WDF content on the blogs page. So thank you. I encourage you to go to the forums. There's a hardware developer forum, and I'd encourage you to give me session feedback. And thank you so much for hauling out here. If there are any questions, we got like 3 minutes, or there's a mic behind you. I need you to go up to the mic, unfortunately. I'm supposed to record this for posterity.
Your drivers of WDF, is it applicable to Windows 8 and ARM platform?
The question is, are WDF drivers applicable to Windows 8, to ARM on Windows 8? Yes. UMDF and KMDF both run on the ARM platform. Okay. Cool. Hey, thank you very much.